Good morning. This is lecture 21 for ECE402. At the end of this lecture handout, as you always get on Tuesdays, there'll be a new homework. And the last lecture, lecture 20 about pitch detection, and also this lecture, mostly this lecture, has a lot to do with that homework that will be due a week from today. So today's lecture is about pitch shifting. And so we did pitch detection last time because pitch detection is very important for most pitch shifting methods. But here is pitch shifting. So the most common way to pitch shift is, as it's labeled here, the technical word is lame, is what this approach is called. And this lame approach here, though, is very common. So what is this here? This looks a little bit like a phase oscillator, except down here you've got a sample file. In this example, I'm just making 16 megs of samples. And so what is this? So you've got a rate that corresponds to the frequency register in a phase oscillator, except here it's kind of funny because you've got the binary point is not at the left, but it's 24 bits of integer and then 8 bits of fraction. In this example, you could set up this example differently. If you had more than 32 bits to work with, you could certainly do things differently. It's just an example. So here you have this rate, and it's a 32-bit number. You have a 32-bit adder. This is the index into the sample file. You start off at 0, and then depending on your rate, you step through this faster or slower. If your rate is 1.0, then you will step through it at the original recording rate. But if your rate is higher than 1.0 or lower than 1.0, you'll step through it at a faster or lower rate. So if you step through this file at a slower rate, if your increment is less than 1.0, or in this case here in hex, it would be all zeros, and then a 1, and then 2 0 hex digits, if we have the binary point there at 8 binary points, 8 behind the binary point. So if you have 1.0 here in this fixed point notation, then you get the original samples file back, and that's fine. Now let's say you have 2.0. Well, that means you'll go through the file twice as fast, and hey, it'll be an octave up. But lots of things go wrong with that. It'll be an octave up, but as it says up here, what happens to the vibrato rate? If you step through it twice as fast, any vibrato that's present in there is going to be twice as fast. What about the onset time? Well, if you go up in pitch, then your onset time, your attack time, is going to speed up, which is undesirable. Just because you're playing higher pitch doesn't mean you want to have a faster onset or a faster vibrato. What's going to happen to your note length? If you have a note recorded in here, it's going to last half as long as if you go up an octave, because you're stepping through it twice as fast. So you're not just pitch shifting, but you're doing all these other things. Worst of all, you're doing the spectral changes. And the spectral changes, when you do this kind of thing, you get this chipmunk effect. Well, let's look at what those spectral changes look like graphically. Let's say at rate 1.0, I just sort of sketched this here just to give a general idea. But let's say your rate was 1.0, and at the original recording had a spectrum that looks like this. I made part of it red. That's this little bump here. And then it has some wiggles in the spectrum. So let's pretend that's the spectrum. If you were playing back at twice an increment of 2, rate 2.0 or an octave up, what would happen to your spectrum? The pitch would go up, but look at what happens to your spectrum. This little part here is way stretched out now. And all the stuff that was above the quarter sample rate, if you go by a factor of 2, then that's all going to alias back. So you'll get this aliased mess here because you're just hitting every other sample is all that you're happening when you do rate equals 2. And so the frequency content of the signal just gets messed up because when you skip every other sample, what's going to happen to your spectrum is it's going to stretch out. And then by a factor of 2, so that you get the spectral envelope stretches out, and you get aliasing for half of it. So that's if you go up in rate. it stretches out here. It's a little bit akin to, well, anyway, yeah. So you can think about this. If you've got questions about it, email me. If you go at a rate of 0.5 to go down an octave, then this part of the spectrum here squishes down. You don't get aliasing, which is nice, but well, or you sort of do. But what happens is all of this stuff off of the half sample rate now only goes up to the quarter sample rate if you go down an octave. And then you get the reflected version of that, like you learned in 310. Why is this? Well, you're repeating every sample twice. I mean, that can't be good news, right? You're just sitting on the same sample value twice. So you get this kind of effect. You get a copy of the spectrum in the audible range. Now, since your DAC is still cutting off up here, you actually hear all of this high frequency gunk when you go down an octave. So not only are the resonances of the spectral envelope here squished down, but you get an immense amount of high frequency junk that really shouldn't be there. So this is a very bad way to do pitch shifting. It's common because it's easy, but it's not very good. One thing you can do, and you might have thought of, is to interpolate, fractional interpolating between the samples on the output here. So when your index here has a fractional part, instead of only using the top 24 bits, use the bottom fractional bits to read up 2 samples of your linear interpolation. Again, that makes it a little bit better, but all of these problems still persist, right? You still have your vibrato rate speeds up or slows down depending on if you're pitching up, shifting up or down. Your onset time decreases when you shift up or increases when you go down. Your note lengths change with the pitch shift. And your spectrum, you still get this chipmunk effect. Now, if you're wondering, what does this sound like if I do different rates? A rate of 2 is a lot. If you do a rate of 1.06 or something, about a half step up, you might not notice too bad. This will stretch out a little bit. You'll get a little bit of aliasing up here, but it won't be too bad. I want to show you a sound example just to see what this sounds like. This one is actually sort of faked in that did this with additive synthesis. So with additive synthesis, you don't actually get this copy of the spectrum. All we're listening to is what happens when you compress and when you extend the spectral envelope. So this is an example of just what does this, without aliasing, what does this sound like when you expand or compress? That's one of the things that this homework assignment, the Lent algorithm, the paper is called Formant correct pitch shifting. What does that mean? Well, the resonances or the formants stay in the same place when you pitch shift. They don't get squished down to lower frequencies or stretched out to higher frequencies, as happens here. So I'm going to play you this familiar phrase, the modeling phrase that you've heard before, but this time without any sort of correction, so that you're hearing the stretch or the compress of the spectrum as you change pitch. That's called the chipmunk effect.
Did you ever have a feeling that you wanted to go and still have a feeling that you wanted to stay?
So you have this effect that when you go up high in pitch, it sounds like, well, the resonances, as you go up in pitch, the resonances get spread farther apart. It's almost like your head is shrunk as the pitch goes up. And as the pitch goes down, it's almost like your head expands. So listen again for those effects.
Did you ever have a feeling that you wanted to go and still have a feeling that you wanted to stay?
Now we can do a very similar thing, but this time do it formant correct. So this is just showing you what happens when you leave the resonances where they're at and you change pitch. This isn't exactly what happens in a person, but it's much closer. I mean, after all, if you're going to sing a higher pitch or a lower pitch, your head doesn't get smaller or bigger, your mouth doesn't get smaller or bigger. There are some other changes, and there are certainly nonlinear aspects to singing and to speech, but this gets a heck of a lot closer, as you will hear.
Did you ever have a feeling that you wanted to go and still have a feeling that you wanted to stay?
So again, if you want to go back and listen to that. The second one was much better because you didn't have this effect of the spectrum being stretched out and squished back. But this example, we're only doing formant correctness. We're only showing this effect. It would be much worse if we'd used this algorithm where also the whole phrase would just be faster if you'd gone through it faster, and so on and so forth. So what you're hearing there, that the purpose of that example is just to show you what happens when you aren't formant correct, as the paper says, or when your formants move positions with your pitch shift. That's when you get that chipmunk effect. All right, so that is the lame technique. That's just stepping through your samples file slower and faster, even if you do linear interpolation. Lame for all these reasons. A better technique that you can do is to insert zeros. Now this really only works for some speech sounds. For acoustic instrument sounds, it generally doesn't work so well, and I can show you why. If you assume a speech sound, you got a glottal pulse, and then it dies out. And then you got another glottal pulse, and it dies out. You got another glottal pulse, and it dies out. This is because there isn't a long resonance, resonating time in your mouth. So by the time the next glottal pulse comes along, most of the energy of the sound has died out. Okay, this is very much different, say, if you have an acoustic sound where the waveform maybe looks like this. Where it has, it dies out very slowly. In fact, in a sound like, say you plucked a violin string, and you could easily hear it ring for many seconds, maybe 10, 20, 30 seconds after you've plucked it. But that's not true for your voice. If you go up 10 seconds, even 1 second later, you don't hear much because up dies out really fast. There is not that there's not that resonating effect in your mouth like there is in a violin body or in other musical instruments. All right, so if you have voice here and you want to lower the pitch, you can do this really simple trick right here where it's pretty close to zero anyway. They're pretty small values. Just insert some zeros. So now you move these two apart, you just insert some zero samples. And here you do it again. You move them apart and insert zero samples. Depending on how many zero samples you insert, well, you get a lower pitch because, right, your glottal pulses are now farther apart. And while that's a quick and cheesy way of doing things, it's actually quite good as formant correct. Why is that? Well, if you were to step through this at different rates, all these little wiggles would stretch out. If you're going to say step through it slower to go down in pitch, all these little wiggles would stretch out. This decay rate here would be slower if you just step through a samples file slower like the lame method up there. But if you insert zeros, this decay rate and all these little wiggles are still the same speed. It's just how often the glottal pulses come. That's what changes. So what that means is these wiggles here and how fast this dies out, that reflects the mouth shape, the resonances of the mouth. It depend on the mouth shape, right? So the resonances or the decay rates of the various harmonics, that indicates mouth shape. And by just inserting zeros, you're not changing the mouth shape or size. The mouth shape is the same if you insert zeros, and that way it's formant correct. You can also do a similar trick if you want to go up in pitch. You cut out some samples here, move things closer together. You do that near zero at the end of each. And again, you can get passable shifts for voice that don't get the chipmunk effect. But a much improvement on that is a Lent algorithm that you're going to read for homework, because it just inserting zeros is a bit of a bull in a china shop approach and only works for sounds where every period most of the energy dies out. But the Lent algorithm is also formant correct. And you're going to read about this algorithm. The way the paper is presented, it's a block-based algorithm. It takes a block of samples, processes them, and then moves on to the next block of samples. What I'm going to show you here in class is the exact same algorithm, but serialized. So this is serialized and also generalized in a way. This is does more stuff than Lent algorithm does, but it's serialized. So what does that mean? Well, the algorithm you're reading for homework has all the same ideas, has all the same stuff, but it's really set up to work on a block of samples at a time, so you can't really use it in real time. Like say you're moving a finger around to change on a continuum, and you want to pitch shift. Even if your sample is pre-recorded, if you're working a block at a time, then there's a very long delay. It makes a block length delay between you move your finger and hearing an effect. So a serialized algorithm like this means you take a block structured thing and you make it work one sample at a time. And you'll see what hopefully, you'll see the difference between this algorithm and that. In a sense, they're the same algorithm, but the one in the paper's block structured. This one here is serialized. So in this algorithm, in the Lent algorithm and the serialized version of it here, you can independently control pitch shifting and time dilation. So if you want to pitch up, shift up, you don't have to change your vibrato rate or your onset time or your note length. Leave it alone. Or say you don't want to do any shifting, you want a longer note. You can change time dilation. So you can stretch out the note or shrink it down without changing its pitch. So those are two independent things. And in a sense, really time dilation or stretching things out in time is just the same kind of operation as shifting pitch. And you'll see in a little bit. When you read the paper, again, it's going to be block structured. That may be easier. There's a block diagram in there and pseudocode and such. That may be easier for you to understand. We'll see. I'm going to show you this first, and then you can read the paper, and it would be really great if you can see how the two correspond to each other. But here we have pitch shifting and time dilation. There's also this other thing you can do in this algorithm here explicitly. Lent is trying to avoid Formant shifting at all costs. You don't want that. You don't want the chipmunk effect. But actually, it turns out that in synthesis, in the Eagan matrix, we found that, hey, if you do a little bit of this, if you stretch this out a little bit or compress it a little bit, maybe not automatically as you change pitch, but just under user control, under formula control in the Eagan matrix, you can get some beautiful effects. Now, anytime you do this, like say you squish it down a little bit to the left, well, you're going to get some high frequency noise. Anytime you stretch out the spectral envelope, you're going to get some aliasing, some fold over here. But as long as you keep that to a minimum and you control yourself, you will do fine. Also, as long as the performer performs the right things. If you're feeling obnoxious, go and try that violin, viola, cello, bass sound in the lab. Play the very highest notes on the full-size continuum, and sure enough, you'll hear plenty of aliasing. So you just don't play those, or if you play them carefully enough. You play them in situations where that aliasing isn't obvious, or you modify the sound and get it to do it a little bit less. So you have a lot of different options there. But yes, aliasing is part of this if you do this Formant shifting using this method. So keep it at a minimum. Don't do too much Formant shifting, and you'll be okay. But just a little bit of Formant shifting can go a long way, hopefully with an acceptable amount of aliasing. So what is this here? We call this synchronous granular synthesis. I'm going to call it synchronous granular synthesis because most people that think of granular synthesis aren't thinking of a serialized Lent algorithm, your homework algorithm, at all. Like I say, for homework, you can read this Lent algorithm. It's block structured as it's presented. It works on blocks of samples at a time, like an FFT would work on a block of samples at a time. But this is serialized, and in order to serialize it, made a granular synthesis. Now, granular synthesis, what does that mean? You take windows of your original sound and windowed little parts of your sound or grains of your original sound, and you play them at different times. Maybe in a different order, maybe with different time spacing, whatever you got. But granular synthesis, most commonly you will hear it or recognize it as something where there's a lot of randomness in it. And we'll talk about that next lecture. But in this lecture, we're talking about synchronous granular synthesis, where synchronous just means we're really carefully choosing the grain times. No randomness here. This is grain times super carefully chosen in order to implement a serialized version or a sample-by-sample version of that Lent algorithm. So you carefully calculate the start time of each grain. Carefully here is a loaded term. It means you got to start grains accurate to a fractional sample. You can't just round to the nearest sample all the time. You got to do fractional sample accuracy. You'll see what that is in a second. You carefully do the grain duration, and you carefully do a formant shift. Only a little bit of formant shift, but you can do formant shift. So just to clarify here, because some of you have seen, well, it's more general than the Lent algorithm that you're going to be presented. It's not only serialized, but has this formant shifting, a few other features. Also, it's more general than SOLA, if you've seen that in other classes. So, oh yes, in the Eagan matrix, this is called Harman. It's a Harman bank, which Harman is short for harmonic manipulator, because, yeah, you can... well, we'll get into that term a little later. What are you manipulating about the harmonics? But okay, so we have this thing here, and okay, so in this thing, there's fundamentally two use cases when you're doing this one sample at a time, serialized. The first one is a live case, where you have new samples coming in and you want to process them as they come in. And you want to pitch shift what's, they say, being sung on a microphone. Last lecture, in lecture 20, the You Are My Sunshine was done in that sense. And you'll see in here there's some minor variations of the structure depending on which one you're doing. In particular, what's in this memory varies. Number two is the one, case number two is more like the one at the top of the page. And it's the one in that violin, violoncello bass sound I played on the very first lecture. Or if you're on YouTube now, you can just search for that. That is done with a number two case, where this data, instead of being a circular buffer that keeps getting filled by the microphone, this is just one set of recorded samples. In our case, we don't use very many recorded samples. In our case, 150 milliseconds is enough for us here to do great things. So 150 milliseconds of samples, that's not much. I mean, that's, you know, it's more than an eighth of a second, but not much more. And that's just one sample. So this is not a sampling technique. It confuses people sometimes because you take a single sample or a part of a single sample of a note, that's what you use for your raw material. But this particular technique here can in no way be considered sampling. In sampling, you have lots and lots of recorded material. Here you only have 150 millisecond snippet that you then manipulate. All right, so that's how the violin sound was done, for instance. So what are we looking at here? We have this thing we call a grain generator. The left side of this here makes a 2-period window for our purposes here. So you want, just like you did in the short window method, 2-period windows are the shortest window you can make. That's useful. And since we want fast response, we serialize this in order that you get fast finger response and such. A 2-period window, shortest window, is great. So this side, its job is just to generate a 2-period window, and this side's job is to deliver a sequence of samples from memory, the ones that you want to have windowed. And all that gets added up. So basically, this whole thing here makes a windowed segment of whatever is in memory. And if you, it's making a windowed segment of some part of this. So let's look at the left side here first. This thing here, WN, is for the window, that's the increment, kind of like Fn, right? You recognize the structure as a phase oscillator, so this is the increment that you're going to take through the window table. If you want to go through the window table faster, then, or in other words, if it lasts a shorter time, or in other words, if you want it wider bandwidth, or if it's going to be wider bandwidth, all those things are different ways of thinking of this. But if you want the window to last a shorter time, you put a bigger increment here. If you want the window to last a longer time, you put a shorter increment here. So how do you decide what to put in WN? Well, it's just 1 over the window duration. We want a 2-period window. So whatever 2-period window is for the data you're granulating, that's what you put in here. This register, when you first start this thing up, when you trigger a grain generator, as the terminology goes, when you trigger this thing, say at a glottal pulse or each period, when you trigger this, you have to start it accurate to a fractional sample. So what you put in here is a fractional sample index into the window table. Because, your glottal pulse is probably not going to exactly start on an integer sample. It's a fractional sample. So whatever fractional sample you want your glottal pulse or your period to start on, that's what you put in here. In here you put how long your window you want to be, how long you want your window to be, 2 periods. And that makes your 2-period window. So as the notes over here go on each period or each glottal pulse, if you think of a speech-like thing in synthesis, you trigger a grain generator. You trigger one of these guys. And at each period, you have to set this here to the fractional sample that you want to start your window at. And then here is 1 over the window duration you have to put in there. You also need to do the fractional sample in here for whatever is in this memory. Right? In this memory, you either have past samples, it might be a circular buffer, use case 1, or in use case 2, it's just something that was pre-recorded in here. In any case, you want to say exactly where to start in there. The starting sample number and also the starting fractional sample number you got to put in there. That's where your 2-period window's data is going to start. That's what's going to get windowed. And then here is you put an increment, how fast you want to step through that. Now this is data, this is different than a normal wavetable in that this is data direct from a microphone, either that or previously recorded from a microphone. So if you want to go through this data at the original rate, you put in this hex value into FN. Why? Because that's an increment of 1, right? You're adding 1 here, the top 12 bits, you're going to have 1.000. If you have this here, the top 12 bits is going to give you a 1, and you're going to step through this memory at the same rate that it was recorded into the memory. You can, if you want, other values of FN, instead of using, like in the Lent algorithm, if you want to do exactly what's in the Lent algorithm, you only ever use this FN value. Because you want to step through the original data at the same rate that it was recorded at. That way you avoid all that formant shifting. You get the, quote, formant correct thing. If you do want to have a little bit of this, though, where, as I had on the top of the page, where you actually stretch out the spectral envelope or compress it some, you can use values near 1. Don't go wild with this, but you can use values near 1, but you can change some of these fractional bits here, and that way do a little bit of stretching and listen to it. If you don't get too much aliasing, that's good. So that's what this comment down here says. This is when you trigger one of these grains, besides setting these 2 things, you also have to set here, where do you start in the recorded data? And then it's a spectral shift. How fast are you stepping through it? Normally, just this hex value, 001, 0000. But if you want to do formant shifting, you a slightly different value. All right. So what else does this say here? Yes, if you do a spectral shift, you got to watch for aliasing, so don't do too much of it. But do understand that the spectral shift is important. It's a way to get timbre changes that are super, super important in good Eagan matrix design. Here, like in the phase oscillator, we say top 12 in this example here. This is what actually is implemented in the Eagan matrix. That's why I'm giving you this. But you do top 12 here. Oh, is that right? I don't want to lie to you. Actually, I think I do this in floating point math. Never mind. But in any case, instead of just doing the integer part of this, you can use a fractional part and do interpolation between these samples. You want to do that. Remember, again, this interpolation is extra important here because in a normal phase oscillator, you have 4,096 samples for just one period. But you don't have that here. If this came from a microphone, your period might only be 100 samples or 150 samples or 80 samples. It's not going to be a whole lot of samples. It's not thousands of samples. So since this is representing, this has way fewer data points per period, you really need to do this linear interpolation or you'll be very sad. All right. So that's what this use bottom 12 bits for linear interpolation. So again, for this memory, there's 2 use cases here. Use case 1 is what's called live in the Eagan matrix. And that's when this memory contains the most recent 4,096 input samples for granulation. You've heard examples of that, like in the sunshine. Also when you heard the overtone singing examples in the background there, you were hearing granulated live bell sounds and such. So that is used there. This is a more difficult one. The one that's more commonly used and a little bit easier is use case 2, where you have a pre-recorded snippet. So that's more like at the top of the page, but in the Eagan matrix, you just get a choice of some pre-recorded snippets, and they're only 150 milliseconds long, so they're very short. And what you're going to do then is granulate different parts of those snippets and hopefully get some good effects. All right, I want to play you some sound examples here. The first one is Summertime, and again, keep in mind, I mean, to my ear, this sounds quite good. I mean, it's a cute, a little bit silly, lighthearted example, but it sounds quite good. This only has 150 milliseconds, so a fraction of a second, a fraction of a note of a trombone sample. And by granulating it, doing time dilations, how do you do time dilation? Well, you just start, if you want to spend more time in one part of the sound, you just start when you trigger your grains. You start grains that one time of the, hang out in a part of the sound. When you set this initial value here, each time you trigger a grain, hang out in that part of the sound. It's up to you, right? It's very important you see this here. The pitch U here is not this F sub n. This F sub n has to do with formant shifting. The pitch U here is the rate at which new grains trigger. So if you're triggering new grains at a low rate, you get a low pitch. If you're triggering them at high rate, because on each period you trigger a grain. So depending on how often you do that, well, that's the pitch U here. But if you want to do time dilation, you can wander around in different parts of, say, use case 2 of different parts of the recording and use the different parts of the sound. So here again, Summertime, first time 50 milliseconds trombone sample. You'll also all of these samples are all these examples that I'm going to show primarily as a core of it use this this serialized Lent algorithm you're looking at here, or synchronous granular synthesis, but they also use other features. So if you're interested in any of these, look up the sounds and study them, because, for instance, in the Summertime, there's also some very clever use of filters and of other effects. But the core of it is 150 milliseconds of a trombone. That's then manipulated, formant shifted, and made to sound different ways. So in that example, you heard trombone-like timbres. You sometimes heard the trombone sounding like it was muted, and that is a filter effect. But you also heard it sort of change gradually sometimes into a more French horn-like sound, and that is just this formant shift control. So it's a very important kind of control to have to move around the formants and get those effects. Now I'm going to play you another one. This is a Tal kalimba, which is, in this case, it uses two 150 millisecond kalimba samples. I'm going to play you those samples first. I'll play you the example first. And I very much like this example. Is this the right pitch shifting method for a kalimba, for a thumb piano? Maybe not, but it's awfully beautiful and I think musically quite intriguing. if you're at all familiar with thumb piano or with a kalimba, you know, well, it doesn't do slides like you're hearing here, but it's unmistakably that kind of sound. Of course, on the continuum then, and with this serialized Lent algorithm, you can cause it to do slides and all sorts of things. When you do extreme pitch shifts to very low frequencies, you're hearing how far, you know, these far apart triggers of this, because every period is so far apart, you're actually hearing far apart triggers of those periods, and it sounds almost frog-like. So it's an interesting kind of pitch shift for it, but makes a nice new sound. Now, just as reference, this is the source material, or the two source samples that was all based on. So you just heard them there. I'll do them again. So yeah, so 250 millisecond samples, and that's the kalimba. So here's another example. Here we have 150 milliseconds of three different things: a bell, a drum, and a reed. This is using the sound called Timbral, I think. It's one of the specialty sounds inside the continuum. Play around with it sometime. And, you know, most people play it, and it's kind of boring renditions of lame, lame sort of just too plain sounding morphs. But if you play with the parameters enough, you can come up with some really interesting sounds. In this case, the source material was 150 milliseconds of a bell, 150 milliseconds of drum, and 150 milliseconds of reed, none of which you can hear, or at least I can hear, in the resulting piece of music after they've been manipulated and dilated so much. But it's a beautiful sound. For lack of a better word, an ethnic sound, because you can't really place it, so you call it ethnic. So I turned down the volume at the beginning there because, well, I don't know until later if the sound turned out here. If the sound is bad, listen to the sound files that came by email to you so that you have a higher quality of them. I'm going to play one more example here. This is called Three Pieces of String. It also uses a violin sound, uses the 150 milliseconds of violin sound. But in this case, Ed had some very different sound design and performance technique. In this case, he's using both hands to play his continuum, but the left hand doesn't play any notes. It just provides additional control over the information from the fingers in the right hand. So you have a left hand, right hand separation. The left hand is in the area we call the touche. If you remember our beginning lectures of the En Martineau, the left hand was just controlling more stuff about what you're hearing from the right hand. So that's what's going on here. And that left hand, right hand separation sometimes actually gives you some very different kinds of sounding things. And especially if you're trying to do things that are sounding a bit reminiscent of, say, violin or the string family, where you do have a right and left hand separation, those instruments, it can also help if your sound design incorporates that kind of thing. So I'm going to play a little bit longer of this. Again, listen to the link to the original if the sound isn't good. This is good enough string synthesis that it's the best I've ever heard from synthesizers. And it's good enough that even professional violinists or string players will listen to it and not guess that it's electronic. So if you can listen with good headphones, that's great. But they also, of course, can tell right away it's not actually a violin. They figure it must be some other ethnic bowed instrument. Okay, well, that's part of a longer piece. I very much encourage you to listen to that, to the whole piece. There will be a link at the bottom of the video, too. I'm not sure if I can include the whole recording in email. It might be too big. But in any case, yeah, that's quite an impressive use of this serialized Lent algorithm with very clever formulas controlling all of these different parameters that you see here. All right, so I want to talk about this algorithm, though. We've been talking about grains and time domain. And while that's fine, it's really good to think of this algorithm in frequency domain. And in fact, in the Eagan matrix, it even has sort of an Eagan frequency domain name to it, namely the harmonic manipulator, as opposed to the grain manipulator. So, as an introduction to this, I just want to do a little bit of a review of things you already know, and then get into trying to explain why this works, why the synchronous granular is so effective. In general now, if you have a single impulse, you know the Fourier transform of that is a flat spectrum, flat spectral envelope. There's energy, equal energy everywhere. And if you have an impulse train, you also have a flat spectrum, but you only have the certain frequencies present. What are those frequencies? Well, they depend on the repetition rate of the impulse train, right? And think about that. This is things you already know, but think about that because it's very important for understanding this next part. All right, so in time domain, if you have a single grain, a single two-period grain, it's going to have some spectrum associated with it. So you can think, spectral envelope, so you can think of that grain in time domain, or you can equally well, or sometimes better, think of it in frequency domain. So here you have this spectral envelope that corresponds to this grain. So if you think of this as a frequency domain technique, I think you'll get more out of it. What happens now is, just like here, we had a single impulse, flat, but now if you have a repeating impulse train, depending on the repetition rate, that's the frequency you have present. Well, the same thing happens here. If you have the single grain and you repeat it, spaced by some distance, that repetition rate determines what frequencies you hear, but the overall spectral envelope is exactly the same as a single grain. So the single grain really associated with it has its own spectral envelope. Now, if you listen to this a single grain like that, you'll hear something like you don't hear much. It's just a little windowed thing. So in that sense, single grain isn't that useful, but it's useful to think about its spectrum because when you repeat it, you get the same spectral envelope. And if you repeat it at different rates, then you get the different fundamental frequencies with harmonics here, right? And depending on how fast you repeat it, like here, you're repeating it at a slower rate. So you have a lower fundamental in harmonics. They're all at the amplitudes, though, of whatever the spectral envelope is of that each grain of the grain. If you repeat it at a faster rate, then you get a higher frequency, and so on and so forth. If you repeat at a fast enough rate, you of course have overlapping grains. That's why you need lots of grain generators. In fact, since they're two-period grains, if you synthesize back at the original frequency, you need 2 grain generators. If you want to go up an octave, though, you need to overlap twice as much. You need to get 4 grain generators. If you go up 2 octaves, you need 8 grain generators. And so very quickly, 16 grain generators. It's 2 to the end. So 2 octaves up, 1 octave up is 4 grains, 2 octaves up is 16 grains, 3 octaves up is so very quickly you need lots and lots of grain generators. It's actually sort of the opposite in some sense. It's almost like I mentioned this at the very bottom, I'm skipping ahead here, but you can think of additive synthesis as decimation and frequency synthesis. Because when you're decimating in frequency, what does that mean? Well, you're taking really narrow frequency bands, in fact, sine waves, and they last a really long time, but you're seeing how each sine wave goes over time. You can think of this synchronous granular as sort of the opposite, if you want, where you do decimation in time. Because what are you doing? Well, you're looking at tiny little pieces of time instead of tiny little frequency ranges, and then seeing how those tiny little pieces of time change. They have opposite issues when you're playing very low notes in this synchronous granular. It's very cheap because you have a grain and long quiet, grain, long quiet, grain, long quiet. So low notes are very cheap because you have non-overlapping grains, where high notes are very expensive because you might have to have as many as 64 overlapping grains all the time just to play your note, one note. Additive sine wave synthesis is the opposite. If you're playing very high notes, then you don't need very many sine waves because hey, there aren't very many partials until you get to that sample rate anyway. So, but if you want to play very low notes, you might need hundreds of sine waves or partial generators to play the sound. So yeah, so it's kind of an interesting comparison between this and additive sine wave synthesis. Okay, so I hope this makes sense here. But the spectral envelope here is in red, and it exactly matches this. Now, when you play the grain repeated closer together or farther apart, you get different frequencies, but the spectral envelope doesn't change. In other words, there is no Formant shifting. It's, quote, Formant correct. The only way you're going to get the formants to shift, to get the red thing to change, is by stepping through the individual samples in here at different rates. And again, look at the grain generator, you can see we do that. All right. So this example here shows a pitch shift, right? You just take the grain and you repeat it faster or slower. Now, what about time stretching? Well, time stretching is just how fast you make it through the sound. So eventually, you're not going to use exactly the same grain all the time as we did in this example here. You're going to take grains from different parts of the sound. So as you go through the, if you want to do time stretch, well, you just go through the sound where you pick your grains from. You progress slower through the sound for that. If you want to do time compression, you skip faster through the sound. All right. So I want to say one other thing about this granular synthesis, which is about morphing, because you already heard some morphing sounds, like the timbre morph sound. You heard the thing that I called plucked ethnic. Here I want to say, what is, with synchronous granular synthesis, what is morphing? Well, if you have two different grains from different sounds, so this is one sound's grains, and you trigger them exactly the same time as another sound's grains, exactly triggered at the same time, so they exactly are synchronous, then, well, you get the sum of this thing. But as long as you trigger them exactly at the same time, remember, any repeating waveform can only have harmonics of the fundamental. So both of these are going to have the exact same frequency harmonics, and when you precisely trigger at the same time, the partials have identical frequencies. So because you don't get the beating between partials, the mix is the same as a morph. So this is very much like the spectral matching synthesis we did with fixed wavetables. If you exactly time each period the same, then a mix is the same as a morph. I want to show you some sound examples here, some more sound examples of morphing. So all this is really, it's just synchronously playing grains from two different sounds at exactly the same time. You can find these sounds in the library and study them if you like. It might be an interesting final project to figure out how these work, or figure out some other part of the sounds. In general, when you study the things that have Harman banks in them, the best ones are usually combined with other filters, or sometimes with other physical modeling techniques like Big Bang, to get the best results. And of course, like anything else on the continuum, or anything else where you play interactive in an acoustic instrument, the performer really matters, as how you get a beautiful sound out of it. Just like not anybody can play beautiful trumpet, even if they can get notes out of a trumpet. Keep that in mind here too. It's not just your sound design. You're not just pressing a MIDI keyboard, starting and stopping things. You're really interacting with the sound. Okay, sound example, viol blow, which is a really unattractive name. But anyway, it morphs one 150 millisecond viola sample and 150 millisecond oboe sample. I kind of like this. It's not perfect, but it's pretty good. One thing that's interesting is any note that starts as an oboe, your ear has sort of this hysteresis. You want to keep it being an oboe, and an oboe's timbre might change a bit, but for you to actually say, oh, now it's changed to viola, or vice versa, when you start as viola and you want to change to oboe, if you start as a viola sound, then it takes a while. Anyway, it's a very fun one to play around with on the continuum, because at first you clearly hear the viola and clearly hear the oboe, and can very conscious when they change, and after a while it all sounds the same. It just sounds like one instrument with timbre changes. So it's very interesting how psychoacoustically that works. Here's a viol blow. And here's another morphing sound. It's I think a wood noise and a clarinet, but he called it, Ed Eagan called it stick clarinet. And I think you're supposed to sort of imagine this medieval instrument that's really hard to get a sound out of. Kind of like a crumhorn. I had an aunt who, or I still have an aunt, but she was, when she was younger, was one of the nation's best crumhorn players. And it was always pretty entertaining to watch her play that instrument. You know, she'd be at these Shakespeare festivals or whatever she was at playing this instrument, and she would be blowing really hard and really working hard, and you'd hear this come out of the instrument. Anyway, so this is this medieval version of a clarinet. It's imaginary, of course, but it sounds like a clarinet that's just really hard to get a sound out of and has its own sort of imaginary beauty to it. All right, well, the next page will have the homework assignment on it, and that's due a week from today. Thank you very much.